All right, welcome. So I do want to just continue in this video by using the tools that we've been preparing to continue talking about sorting algorithms. We looked at in the last couple of videos the bubble sort algorithm, which is the simplest sorting algorithm from the machine's perspective. And now I want to look at the selection sort algorithm, which is one of the simplest sorting algorithms from a human perspective. So let's take a look at some pseudocode. So I've got restated here the sorting problem, but we already went over that in an earlier video in some detail. We're just getting some sequence of integers, and we're going to permute them. That is, we're going to put them into a different order such that, well, which order here? Ascending order is the order that we're interested in. And so in this video, we're going to be looking at the selection sort algorithm, and I've got some pseudocode here presented for us. Let's just take a quick look. So as with the bubble sort algorithm, and with most sorting algorithms, we've got a nested loop structure here as well. That means when we want to prove this correct, that we're going to use the same technique that we did in the previous videos. We're going to have an inner loop invariant. We'll deal with that one first, and then usually we'll rely on the inner loop invariant to prove the outer loop invariant in the same way that we would use a loop invariant to prove a proof of correctness, which of course is the final piece of that puzzle, the final step that we will do. So for this problem, or for this video, I'm going to be looking at this version of the pseudocode, this nested loop structure, and trying to argue that it is correct. So let's go in and see. We'll put it through our brain compiler first. That is testing our own built-in intuitive compiler to see if it works. Of course, we rely on that a lot when we're doing our programming. When we design these, we rely on our internal compiler. And then, of course, we debug by relying on the actual compiler. But let's take a look at this one and see how it works. So our outer loop is a loop I from 1 to n minus 1. And we saw that was common in bubble sort as well, that we might, instead of going 1 to n, we might end up with this n minus 1. The minus 1 coming in because when we're doing comparisons, we usually need a pair to do comparisons. So in bubble sort, where we were just looking at one next to the other, we stopped at n minus 1 because n minus 1 would look at position n. That would be its pair, the extra one that we would look at. And so it's a similar idea here, that we're going to stop one earlier before we get to the end. Okay, that's the outer loop. Maybe we'll verify it. In fact, we could run it all the way to n, but when we get to our analysis, we'll see that that maybe saves us a little bit of time. Okay, once we're in our loop, what do? Well, we set m equal to I. Now I'm going to be clear here. In my pseudocode, I've used just m. It just looks a little bit nicer on my slides. But if I was actually writing this as code, I'd usually use a better name for some of these variables, n and m and so on. And here, m is going to keep track of the index of the minimum element that we're looking for. So the phrase "so far" comes in, as we've used this before in our loop invariants. The loop is usually keeping track of something so far, and in this case it's going to be the minimum so far, at least out of a sub-list of elements that we're looking at. So m is going to keep track of that index of the minimum so far. If I was writing this in a program, I usually call it mindex, because I think that's clever and I think I'm a clever person. But that means just the index of the element with the minimum value. So again, that's what m is. Again, in pseudocode, or at least as I've got it here for ease and for how it looks, I've just reduced it to m, but in real code, we'd probably give these better names. Okay, so m is supposed to keep track of the minimum so far. What do I initialize it to? I initialize it to I, which, well, we might have to think about how these loops are working in together. One's nested inside the other, how they work one in another, and maybe we'll get to that in a second. But initializing it to I the first time around means initializing it to 1. And that's sort of standard. If we were just trying to take the minimum of a list, there's a couple ways to do it, but a very standard way is to initialize it to the first element and then start your comparisons after that. So that's what we've done here. And if you want to, jump back to that minimum video that we made, a handful of videos ago, and take a look and see, hey, we're basically, this inner loop is really just doing that minimum algorithm that we already looked at, with one sort of major important change, which is instead of starting at 1, we're starting at I plus 1 in our iteration. Actually, let me back up one step. In the normal iteration, we initialized off to 1 and then we started at 2. That's where the plus 1 comes in here. So here we're initializing to I, and we're starting our comparisons on the next element, which is I plus 1. Okay, so the first time around, that would be initializing it to 1, and then starting from 2 to n, which matches perfectly that minimum algorithm we looked at a few videos ago. Now, what we have here, okay, is very much the same as what we did before, okay? The only other major change between this algorithm that I've got here and the minimum algorithm that we looked at is here we actually are keeping track of the index of the minimum. And I believe in the minimum algorithm, I'd have to go back and double check to make sure 100%, but in that case we kept track of the actual minimum value, not the index, we kept track of the value. And of course both are common ways to solve the minimum problem. In this case it's the index, because what we do after we find the minimum element is we swap it into position I. Remember, the first time around, that position I is the first element, position 1. So what that means is we find the minimum, the first pass through finds the minimum of the whole list and then swaps it into the first position. And then what we'll notice is the second iteration around, when I is equal to 2, we now ignore that first element. Since we swapped the minimum into position 1, we do the whole thing again, but starting at position 2. So at position 2 up to n, we'll find the minimum and swap it into position 2. And then again, we'll find the minimum from position 3 to n and swap it into position 3. And we'll keep doing that every time until we've put them in order. Now, hopefully what you just did is the same thing I just did, is you put that through your internal brain compiler and you thought, yeah, that makes sense. If I select the smallest one and put it into the first position, and then I find the second smallest one and I put it into the second position, and so on, that will sort the list for me. And this is a very standard way for human beings to sort things, in particular sorting cards in a hand. If you've ever played cards in a game like bridge or hearts, where you might be dealt out 13 cards and you want to put them into some kind of order. To do so, of course, you need some algorithm, and a lot of humans use selection sort. The other one humans use is insertion sort, and if you're interested in that, well, we could try and prove insertion sort true as well. Well, that's not a topic for this video, so let's continue. So in this video, we've kind of got this idea now of how the selection sort works, but we want to prove it's correct. Now remember, the proving it's correct gets down to the nitty-gritty, making sure we haven't made any errors, we haven't flipped our signs around. Just because we put things through our mental compiler doesn't mean that it will work when we put it through a normal compiler. Of course that's the case, because it's very rare for you to sit down the first time, pound out some code, and hit run, and it just works. It usually doesn't work that way. Our brain compiler is really good, it's just not perfect. So let's see if we can prove that we've actually got our pseudocode correct to, say, a skeptic, someone who maybe doesn't believe us. Now again, I'm going to just comment on our strategy here first. We're going to prove the inner loop invariant first, then use it to prove the outer loop invariant, and then use that to prove the whole algorithm is correct. So again, that's a couple pieces we need to put together, and it's going to build on our experience already working with loop invariants. So let's continue again, or let's go through that one more time. We need to come up with a loop invariant for the inner loop. So what did we say in our discussion? Well, we said this inner loop was meant to find the minimum. So remember, when we dealt with the minimum algorithm, we talked about the minimum so far. This M keeps track of it so far. So the inner loop invariant should be something about the minimum so far. And if we really want to borrow off the work that we've done before, we should probably go back to that work on the minimum algorithm and borrow from it what the effort we already put in, meaning borrow from it the actual theorem we proved about that algorithm, and then borrow from it the actual proof too. And I'll be honest, when I created these slides, well, it was a while ago that I did that. It's over a year ago, but I'm pretty confident that the way I did it is I literally copied, cut and paste the work that I had done before here so that I could do it again. Now, that's just for me as an instructor trying to save some effort. You know, I don't want to type everything out the same. You as a student, you might want to, you know, go through the effort of not just doing the cut and paste, but cutting and paste is often a very efficient tool in our toolkit for programming. If you're not using cut and paste in your programming, then you're missing out on a very, very important tool. But the other side of the cut and paste tool is you need to know when to use it and then how to modify what you've pasted so that it works with what you're doing now, especially in programming, but also in proofs. So I can't just go over there and grab it and say, look, because minimum worked over here, it's going to work here. And and the important reason is there's some changes to my algorithm here. One, we're starting at I, not 1. Okay, those little bits we can probably make work. But also remember, we're keeping track of the the index here of the minimum instead of the minimum itself. So that means that change alone, again, these are sort of surface level changes that don't seem to impact the correctness, but can we show that? Well, we might want to prove this inner loop invariant separately. So let's see if we can do that. So the loop invariant, we can imagine I've borrowed this from before. Maybe I cut and paste it, but I did have to change this bit about the index of the minimum element. If I remember correctly, before we had something about m being an element of this list and being the minimum element. Okay, being less than or equal to all the other elements in the list. All of that, I'm gonna rephrase it, cash it out in a slightly different way by saying, okay, m is the index of the minimum element of this list. And actually that carries a lot of sort of, we're making use of the phrase minimum element, which we're hoping all of our readers are familiar enough with mathematics to be able to formalize that statement themselves. And then also the index is what we're highlighting here. The index here, because we're using the phrase the index of, it's actually capturing the little bit of making sure that we're not picking something outside of this set. By picking an index of something in this set, we're forcing ourselves to only pick something in that set. And so what that means is we don't have to add extra language here to our theorem saying, oh, and be careful that m is not the index of something outside of our set. It's very clear from how we've expressed this that that's what m is intended to be. Okay, so m is the index of the minimum element. Now let's look at that set. I keep saying set, but it's actually a sequence, the way I've written it. We have a sub I plus 1 up to a sub j. Now, we need to be a little bit careful here. What's going on here? Well, j is the counter of our loop. So if we go back here, remember this is our inner loop. J is the counter of that loop. And so what is I? Well, I was the counter of the outer loop, and it's actually something that we're going to take for the inner loop as a constant. We know it will change every time we hit this inner loop. But while we're talking about the inner loop, while, say, for instance, the inner loop is running, I is fixed. I doesn't change while this loop goes. So we're going to just treat I as a constant. And in the first, and when we did the minimum proof before, that constant was 1. 1 here, and when we plugged it in here, it was 2. Well, for now, we're just going to leave it as I. Give it that name I. Okay, so again here, in the original proof, if we were cut and pasting here, we would have had A1 and A2 up to AJ. So I've gone ahead and modified this to make sure it's correct to say AI and AI plus 1. Okay, remember I in the first iteration would be 1, so this matches up correctly. Okay, so the J here, remember, this is the so far bit. The inner loop is keeping track of the minimum so far, not up to A sub n, but it will get to a sub n. We will eventually get there, and let's just verify that that's the last point in our trip. So after the whole loop is done, we might have something stronger to say than just this region, but after iteration j of the inner loop, this is what we've found the minimum of so far. Okay, let's see if we can prove this. So again, like we've done before, we're going to rely on induction, which is one of our more powerful tools of proof that we've been looking at. And we're going to do this induction on j, which was the counter or the iterator of our inner loop. Now we need to pick our base case, and I've mentioned before we can do the base case of after the first iteration or before the loop starts. I personally prefer before the loop starts, usually because it's an easier thing to prove. Usually before the loop starts, we haven't done anything yet, so there's nothing to talk about. We just say, look, nothing's happened yet. So what happened before the loop, before our inner loop? Okay, so that means we're inside the outer loop. We've already got I started, but we go to that first step. Well, the first step is we set our m equal to I, which is the first element, right? So let's just go through here the reasoning that we have here. I've said j equals I. That's before the loop because our inner loop starts at j equals I plus 1. So remember, this is before the loop. So that's all I've got here. Okay. So prior to the loop, we set m to be I, which is the index of the minimum element. Now let's plug in here. If j is I, then j is I. This is just ai to ai. That's just ai. Well, if m is equal to I, is that the minimum element of this sequence? For sure it is. Okay, there's only one element in that sequence, so as long as we've selected that index, which we did, it must be the minimum. Okay, so we're good. Check mark, base case is done. What about the inductive hypothesis? Well, the inductive hypothesis is, well, we've talked about what happened on iteration j. Now we want to talk about what happens on iteration j plus 1. So after iteration j is before or prior iteration j plus 1. So prior to iteration j plus 1, we're going to assume the exact same thing that we have after iteration j. So here again, I've used that cut and paste to bring that down. Okay, so I bring it down. What is it? M is the index of the minimum element of this set. Exact same wording. Now, usually what I do here is I say, well, what are we trying to argue about after this iteration is done? Well, now m should be the index of the minimum element of the expanded set that included a j plus 1 in there as well. So this is again just restating what we know. Okay, and now we're going to look at the two possibilities. Now remember, in this step we're going to compare our two terms, our a j plus 1, that's the current element that we're iterating over, versus the minimum so far. That's what m stands for, right? If the element that we have is greater than or equal to the minimum so far, then we make no change. So in this case, we make no change to m, we leave m alone, but we can see it's also less than or equal to this element, so it must be the minimum element of now our expanded set. It was already the minimum element up to here. We've now added this element on as well. Okay, what about the other case? The other case is when our new element is smaller than the minimum so far. That means our new element is the new minimum so far. So we make the change, and indeed we do. We check our code, we do make this change. So in this case, I'm just verifying using this transitivity property. Since aj plus 1 is less than am, and am was the minimum so far, so we know it's less than or equal to all these elements, we now know that aj must also be less than or equal, or aj plus 1, sorry, is less than or equal to all of these elements, and therefore it must be the minimum element of these elements, but also including itself. It will also be the minimum element including itself. So that's the expanded set we were looking for. That's the same set we got to here. So we are now done. So we can say by induction, we've shown that after iteration j, that m is the index of the minimum so far. And that's, again, how I express this last little bit here, minimum so far. So that's the inner loop invariant, which doesn't bring a lot new to the table because it's very similar to the minimum algorithm that we looked at, again, a handful of videos ago. So what that means is a couple changes to make it work here. Probably the critical one is the index and the fact that we're starting out at I instead of at just 1. Okay, let's see how this impacts the outer loop invariant now. So in the outer loop invariant, now we're talking about that outer loop. Let's think just for a second about what that outer loop was. It was saying the inner loop, remember, was finding that minimum element for us in that range, that important range, and then it was swapping that minimum element. That the very last thing we do is we would swap that minimum element into position I. And the instinct we got here, so let's go through how that outer loop went again, is first it moved the minimum element into the first position, then it moved the second minimum element into the second position, and so on. So what we end up getting is after I steps, the I minimum elements will be in the right positions. And we might want to formalize that a little bit more, but let's see what that is. So it says after iteration I of the outer loop, the I minimum elements, so that was the part we had focused in on, the I minimum elements of what? Of the whole list, the whole sequence, are in ascending order in positions 1 to I. Now that bit, that last clause, is allowing me to capture the in the correct positions, okay, and making it more formal. I'm saying those I minimum elements, first of all, they're in ascending order, and they're in the right range of indices from 1 to I that they belong in. If they're in that range and they're in ascending order, then that means every single one of them is in the right position. So here I've just formalized that a little bit more. Okay, so again, like in our previous example in the bubble sort, we now need to bring a lot of things to bear here. We need to, in our proof, rely on the loop invariant that we just finished proving about the inner loop with J, because that's the inner loop that's going to find us that minimum element. Okay, so we have to rely on that. So let's go ahead and do this. Again, we're going to use induction, this time on I, because I is our index that we're iterating over. And again, we'll try to start at least before the loop. And so if our loop, remember, went from 1 to n minus 1, we'll start at I equals 0, which is prior to the loop. Okay. So let's just see what that would have to say then. After iteration 0 of the outer loop, these 0 minimum elements are in ascent. Okay, because the statement happens to be about the 0 minimum elements, there are none. This creates another case where this would be vacuously true, meaning there's nothing we need to prove about. If we need to prove something about nothing, then there's nothing to prove. And so that's what we have here. Again, just setting this up. So I equals 0 is prior to the loop. In this case, it's trivial to see that the 0 minimum elements are in ascending order in these non-existing positions. It's just a trivial or vacuous state. So we can move on from the base case and move into our inductive hypothesis. So in the inductive hypothesis, again, we want to talk about, well, now that we've got things started, what about after one of our iterations? Well, prior to the iteration, this will be true. And so we now want to argue about after the iteration. So prior to iteration I plus 1, what we have stated here in terms of after iteration I will be true. So we'll restate that. Assume prior to iteration I plus 1, and then we'll copy the clause down, or the whole proposition down from above, that the minimum, which minimum? The I minimum elements of this set are in ascending order in these appropriate positions, which again, I've just copied them down to be correct, okay? Cut and paste, you always want to read it over afterwards, verify that it's correct as we just did, but in this case, we just had to merely cut and paste it. Okay, so the next step then is the inductive step. Okay, so we're going to pick up in the inductive step. And remember, that's where we're going to argue about what happens after this iteration, after iteration I plus 1. Okay, so we'll start this up, and let's get ourselves started. Well, we'll start by applying our inductive hypothesis. What did we know prior to this iteration? Okay, well, we know that I minimum elements are in the ascending order. Okay, what do we need to argue then after this? Well, we need to find that next element, the I plus first minimum element, and we need to put it into its correct position. and leave the other ones alone, and we leave all the other ones alone in this loop. If we want to be very pedantic and precise, we might add that into our proof here, although we're going to leave it out for brevity, for the most sake, hoping that our readers could fill that little bit in and see, oh, well, they don't mess around with anything they've already solved, so we don't have to worry about that extra condition. Okay, so what that's saying is we really need to just focus in on this. Can we find the I plus first minimum element, and can we move it into the right position? So the first thing we'll notice, and that might be relevant, is that since the I minimum elements are already in the right position, the I plus first one can only be in position I plus 1 up to n. And that's important because that's where our inner loop is going to do our searching. So we're going to now apply our inner loop invariant. Okay, after iteration j of the inner loop, m will be the index of the minimum element starting at I plus 1. In a normal loop it would be I, but because we're in iteration I plus 1, that's why we get I plus 1 here instead of I. Okay, so remember, in our normal loop invariant, if we went and looked at our loop invariant, this would say AI. But we're applying it to the case where we're in iteration I plus 1, not in iteration I. So we plug in I plus 1 for I, so these two changed. But the upper bound did not change, j. Okay, now we're not worried about any particular iteration of the inner loop except for the last iteration. So in particular, after the last iteration, which stopped when j is equal to n of the inner loop, now m will be the index of same starting condition, I plus 1, AI plus 1, AI plus 2, but now rj becomes n. So that means we've now found the minimum element of those elements in position I plus 1 up to n. And as I just argued a moment ago, since the I minimum elements are already in the right positions, we know that this minimum element we found out of these elements must be the I plus first minimum element of the whole set. Okay, so it was the minimum of what remained, which meant it was the I plus first minimum of the whole set. Okay, great. Well, what do we do with it? Well, when the inner loop completes, we swap that element into position I plus 1. That's where it belongs because it's the I plus first minimum element. So we've swapped it into the right location. That's what we were trying to prove. So we're done. Okay, so by induction, after iteration I, we've now shown that these I minimum elements are in the right position. Okay, well, how are we going to use this? Well, again, just like we applied the inner loop invariant here, we're now going to apply the outer loop invariant to say, okay, well, we don't need to be worried about any one particular iteration except for the last iteration. What was the last iteration? So let's try and put that last proof together and argue that our algorithm then is correct for the sort problem in the same way bubble sort was. So again, in our proof of correctness, we've done most of the heavy lifting in our loop invariant. So that means here we just need to focus on what remains, which is starting with an arbitrary input. So let's just say someone handed us an input sequence of integers like this, okay? And then we want to apply our outer loop invariant. So we're going to say by the outer loop invariant, we know that after iteration I, we've got the I minimum elements in the right positions. Well, how many iterations do we do? We don't do n, we actually do n minus 1. If we did n, there's nothing wrong, because if we did n, we'd say, hey, look, they're all in the right positions. But we also notice we can stop early, because if n minus 1 of them are in the right positions, then the remaining element is the maximum element, and it has to be in position a, n, and that's where it belongs. So all of them are in the right position. So this is just highlighting that we stop early, and we are allowed to stop early. We don't risk being incorrect by stopping early, and so therefore, after iteration n plus 1, or n minus 1, sorry, we've returned the correct permutation, the one that we want, the one that's in ascending order. All right, that's all I had for this video, where we looked at the proof of correctness of selection sort using loop invariant, two loop invariants technically. And I will leave to the next video where we will do a runtime analysis of the same code. All right, thanks for watching, and we'll see you in that next video.